And looking at distributions of data. Today we're going to focus in on looking at probability distributions. Put the laptop away, please. So, beginning of this chapter focuses in on working with just large sets of data. But probability is another key piece that we're going to be doing throughout this section rather than just working with general data. When you're working with probability, though, we're going to be shifting certain things in what we do, because when it comes to working with probabilities, generally speaking, you're not going to necessarily be working with a sample anymore. You're going to be working more with information about a population. Reason being is because you're going to have the situations where you need to know what all of the possible outcomes are. And if you've got all of the possible outcomes, you've got everything that can happen, that is more of a population situation. It's not where you're working with just bits and pieces. Now, the verbiage is definitely different, though. In probability, we don't call something a population. We talk about the sample space. The sample space is the list of all possible outcomes when you're working with a situation. Now, sample spaces can be very straightforward, easy to work with. Others are going to be more complex. It really kind of depends upon if you're working with what are known as simple events, like single things happening, or you're working with more compound events, where technically you're dealing with multiple things happening in that situation. So in order to work with probabilities, one of the things that you have to be able to do is you have to be able to recognize what that sample space is in especially simple events, but in not so complex compound events as well. So we're going to list out that sample space, and we're also going to find the size of the sample space, because if you can't find the size of the sample space, then you cannot do probability. This kind of goes back to what we did in chapter 10 when we talked about combinations and permutations. When we were trying to find the probability of something, we found out all the different ways that we could arrange the things, as well as all of the different ways that we could arrange the things in a specific way that we wanted, and we divided those two numbers, what we wanted divided by total number of options. The total number of options was the size of the sample space that we were finding. We were just finding it in situations where we were grabbing a smaller group out of a larger group. Sometimes when you're working with sample space, it's not necessarily having to do that. For example, rolling a six-sided die. The sample space is all the different things that you can get. Now, assume that this is a typical six-sided die. What can you get when you roll it? 1 through 6. 1, 2, 3, 4, 5, 6. That's my sample space. And the size of said sample space, how many items are in that sample space? 6. A compound event where you have multiple things going on, like rolling a die and then flipping a coin, same idea, slight difference in what we're doing. When you roll a die and then flip a coin, what are the possible things that you could happen, or that could happen there? What, rolling the die was the 1 through 6, right? When you flip a coin, what can happen? Heads or tails. Which means that your sample space with the compound event is you could get a 1 on the die and then a heads on the coin. Or you could get the 1 on the die and the tails on the coin. And you could do that with any of the numbers, right? 2, then heads, 2, then tails, 3, then heads, 3, then tails, 4, then heads, 4, then tails, 5 heads, 5 tails, 6 heads, 6 tails. Size of the sample space? How many different possible outcomes did I have? 12. Could I have figured that out without listing out the entire sample space? How? We've done it in here before. What's the calculation? Six times 2, where's the 6 coming from? Outcomes of the die. Where's the 2 coming from? Outcomes of the coin. So, we did this back when we did combinations and permutations as well. We had those situations where we had a bag full of real and fake diamonds. We wanted to pick out 3 real and 2 fake. And so we found out the number of ways we could grab 3 real, the number of ways we could grab 2 fake, and we multiplied them together. That was a problem from your homework back in chapter 10. As the items get more complex, one of the things that tends to happen is people tend to all of a sudden start missing pieces of their sample space. So knowing the size of the sample space ahead of time can help to make sure that you are not missing any of your possible outcomes within your sample space. Flipping 3 coins. If I focus on the size of the sample space first, what calculation am I going to do? How many individual events are happening here? 3. What's the outcome of the first event? How many outcomes, I should say? 2. About the second event? 2. Third event? 2. 2 times 2 times 2. I should have had a total of 8 outcomes in my sample space. Flipping 3 coins. What's one possibility of what can happen? all heads. Now, when you do stuff like this, I also recommend that you do some sort of organization. I just do different columns for the different number of heads or tails in this situation. So one column for getting all heads, one column for getting 2 heads. What are the different ways I can get 2 heads when I'm doing this? Heads, tails, heads. Or tails, heads, heads. Any others? Heads, heads, tails. Any others? No. Okay, so I move on. That was 1 heads. That was 2 heads. How many different ways can I get only 1 heads? I heard tails, tails, heads. Tails, heads, tails. Last but not least, heads, tails, tails. 1, 2, 3, 4, 5, 6, 7 outcomes. The only outcome I'm missing? Tails, tails, tails. Okay. So, why does this matter? Being able to list out your sample space and know the size of your sample space can help you with finding probabilities. For example, if I wanted to figure out the probability when I flip 3 coins of getting exactly 2 heads, there are 3 out of a total of 8 ways. My sample space allows me to know how many ways I can get the specific item that I want, and the size of the sample space tells me what to divide by. So that's why listing out our sample space and getting the size of the sample space are important. But overall, as we move through and do this, our goal is to step away from the basics of listing the sample space and finding its sample size and really just doing those probabilities. Now, when we do this, we're going to be working with situations where we're dealing with random variables. Random variables, by definition, are numerical outcomes to random events. Now, with my listed sample spaces, 2 of the 3 of these could be defined as a random variable. The first one, the numbers I can get rolling a 6-sided die, could be a random variable. Or, here, I could have a random variable where I'm referencing x, because it's a variable, and it's generally x that we use. X is being the number of heads that we get. The middle one cannot, because that is not a purely numerical outcome. The moment that they got the heads and the tails involved, it's no longer a number. Now, these random variables can come in 2 different forms. Discrete and continuous is the other one. A discrete random variable is one in which all of the outcomes are, technically it gets a little more complicated than this, but essentially it's when all the outcomes are integers. Generally speaking, when I'm going to ask you to list out a sample space, that's most of the time going to be a discrete random variable situation because of the fact, that is, if it's a random variable. It's going to be a discrete random variable situation because of the fact that you're really only going to be listing things if they come out as nice numbers. Because continuous random variables are really outcomes that can be, quote unquote, any specifically type of number. Now, I put any in quotations because of the fact that there's going to be limitations in a continuous random variable, in the sense of the problem itself will limit what type of numbers it is, but the continuous idea really is just saying you're allowed to get things like decimals. It's really what it's focusing in on. Continuous random variables would include things like a person's height, if you're wanting to find the probability of someone having a specific height. My height is not defined as being technically 5 foot or 6 foot. There's decimals in between. Same thing with, I just lost my train of thought there. Same thing with like weights of various things. A person's weight, an item's weight, it might not be whatever. It doesn't necessarily jump from one number to the next number automatically. There's those decimals in between. But in both of those situations, I'm not going to have a negative height. Something's not going to have a negative weight. So technically there are some limitations, but it allows it to be decimals is the key thing for that continuous. So, as long as you can simplify something down as outcomes being numerical, it fits with the idea of a random variable. Again, this one was obvious. This one, technically, I know I mentioned the heads and tails causes issues. It doesn't cause issues if you're talking about the number of them. I couldn't really talk about the number of them here. That's why this one didn't work. Now, with these random variables, we're going to make what are known as relative frequency tables. Now, I mentioned relative frequency the other day, last week, and then a little bit again yesterday in reference to histograms. What technically is relative frequency? How often something happens relative to other things? Often written in what kind of units? Nothing from the histograms? Relative frequency histograms were ones where it wasn't frequency, it was percentages. I know, we didn't really actually do relative frequency histograms yesterday. For the most part, we stuck with the frequency ones. But relative frequency is essentially probability. A relative frequency table is a table that has all outcomes of a random variable with their percentages. let's try that again. You don't flip heads on dice. Yep. That's what happens when I try to reword the problem and not apparently paying close enough attention. Coins. That makes more sense. So create a relative frequency table for the theoretical probability of flipping X heads on 3 coins. Okay, first off, random variable here is X, and 99% of the time it is going to be X. What does the X stand for? Number of heads flipped. So, relative frequency table, 2 columns or 2 rows. In this case, I'm going to do rows for no particular reason other than saving space on my paper. Because if I do 2 columns, that's taking up a lot of room that I don't need a bunch of room next to it. When I need the room next to it, I do make columns. Okay, so X equals number of heads is the first either row or column. And the second row or column is always the probability. Probability is always given by P of X. And yes, that is function notation. P being probability of X. Far too often, I write out P of X in this class and people start multiplying P times X. Nope. P of X. Okay, so X equals number of heads. In a relative frequency table, my random variable, column or row, must have all possible outcomes for that situation. Number of heads. How many heads can I get when I flip 3 coins? 1, 2, 3, or 0. Don't forget 0. So, I need 0, 1, 2, and 3. It honestly doesn't matter the order. I tend to prefer smallest to biggest. P of X column is the probability of that specific X. In other words, this one right here, X is 0, so it's the probability of getting 0 heads. Can you put the laptop away, please? Thank you. Didn't we list off the sample space for this situation? There was my sample space. To find probabilities, it's the number of ways you can do what you want divided by total number of ways of everything can happen. How many ways can I get 0 heads? 1. Getting tails, tails, tails. Out of how many total ways can you have 3 dice or 3 coin flips? 8. So 1 out of 8. Now when it comes to probability, I do not care if you give me the probability as a fraction, as long as it's simplified. I do not care if you give it to me as a decimal, as long as you're rounding correctly. I would generally go to 4 decimal places. This is the same kind of situation we had back in chapter 10 when we did the combinations. I do not care if you give me the probability as a percentage, as long as you should technically give me, there wasn't a decimal after this, that's why I stopped at 3. Generally, the decimal I want 4, but if there's nothing beyond it, there's nothing beyond it. But anyway, the percentage should have 2 decimal places after and should have the percentage on it. Do you need all 3 of these? Absolutely not. Would I ever write all 3 of these for any reason other than it's our notes and I'm trying to say you can have all 4 of these? Yeah. 3 of these. There's only 3. I can count. Dice and coins and 3 and 4. I'm having a day, apparently. Okay. Anyway. All 3 of these are acceptable. Make sure fractions are simplified. Make sure decimals are to 4 places. Make sure percentages are to 2 places with the percent symbol. That's the short of it. Okay. Probability of getting 1 heads. Three-eighths. I'm just going to write the fraction on this one. Probability of getting 2 heads. 3/8. Probability of getting 3 heads. Just messing with me by all of a sudden changing it to the percentage. 1/8. Okay. You might be asked, to graph the probability distribution. Probability distribution is a bar graph when it's graphed. A true bar graph, not a histogram. X-axis is the random variable. The y-axis is p of x. Make sure if it's in percentages, you're putting a percent symbol on that. If you're graphing in decimals, you don't need it. If you're graphing in fractions, you don't need it. What kind of scale do you want along the p of x? Do you want the percentages, do you want fractions, or do you want decimals? Fractions. Fair enough. Okay, looks like I've got 1/8 and 3/8, so I'm going to count by eighths. 1/8. If I'm going to do fractions, though, can I ever write 2/8? No, 2/8 is 1/4. Make sure you're simplifying your fractions. 3/8. Make sure you're counting by a consistent scale. Okay, along the bottom. One of the things that is true about histograms as well as bar graphs is the y-axis is not necessarily 0 for where x is. Zero, 1, 2, 3. In fact, the x-axis on a bar graph does not need to be evenly spaced in the sense of if my number outcomes weren't 0, 1, 2, and 3, if they were 5, 12, and 500, I could do 5, 12, 500 evenly spaced out here. A bar graph, the number you put on bottom is just a label for the bar. Doesn't have to be in a specific order. It does not have to be starting at a specific location. And it doesn't have to be like spaced in any way other than, well, they're kind of evenly spaced, even if the numbers themselves are not. Since it is a true bar graph, the bars do not technically touch. But I make the bars as high as their probabilities, and there we are. Now, there are some key things you need to know about these probability distributions. Some things that I've already written down and even glazed over a little bit. Can be theoretical or experimental. Now, I wrote theoretical already at the top of this page. Create a relative frequency table for the theoretical probability of flipping S heads on 3 coins. Do y'all remember what theoretical probability is? What does theoretically mean? If something happens theoretically, kind of. I'm not saying that one aloud because it's not quite going to get people there, I don't think. If something happens in theory, does it happen? It's generally what could happen, or what should happen. And I change it to the word should because theoretical probability focuses in on all possibilities of what could happen, yes, but it is very specific in the calculation of those probabilities. It is the exact same regardless of who is calculating that probability for that event. If it's not the same, someone did something wrong. We did the theoretical probability for flipping coins because in theory, if we flip 3 coins and count up the number of heads, this is what should happen. In theory, if I flip 3 coins 8 times, one of the times I should get no heads, one of the times I should get 1, 3 of the times I should get 1, 3 of the times I should get 2 heads, and 3 of the times, oh my goodness, 1 of the times I should get 3 heads. I can words. So, theoretical is what should happen. Experimental is what does or did happen. If I legitimately started flipping coins, that is an experimental probability, or I can run a simulation for one. And we're going to talk about that. Probability distributions, they can be discrete, they can be continuous. If I'm having you create a bar graph, that's a discrete one. Continuous graphs are going to look more like curves. They're going to vary a little bit. We're going to get into probability distributions that are continuous, but we're very particular on which continuous ones we look at. The probabilities of different things happening should always be between what 2 numbers? What 2 percentages, if that helps? 0 and 100. Why am I writing? Oh my goodness. It's because I'm starting to talk about an example. If you're working with a situation where you talk about getting 120% of something, that's not probability anymore. The percentages we're working with are specifically probabilities. Furthermore, What should the probabilities add up to? 100%. If they don't add up to 100%, either something was miscalculated or an outcome was missed. So, the other thing that we need to deal with is going to require us running a simulation. Focus in on the last thing we need to get to. Run a simulation for getting X heads when flipping 3 coins with 72 trials. So, if you're wanting to run a simulation, you have to start off with setting up some groundwork of how you're going to make this work. In order to do this, we're going to do it on our calculators. There are different ways to do a simulation. Option 1 is we have coins and we start flipping 3 coins 72 times. We ain't going to do that. Another option is to use your calculator. Calculators are great for running simulations. Grab a calculator if you don't have one. To run a simulation, you need to figure out some basic things first. You need to focus in on a single, simple event within we're going to do it that way. You need to focus in first on a single, simple event from that simulation. In this case, we're going to hone down our flipping a coin 3 times into flipping a coin once. When I flip a coin a single time, I can get either heads or tails, right? What is the probability of getting either of those? They're each 0.5. I need to set up a situation where my calculator is going to give me random numbers, and those random numbers result in numbers that tell me it's a heads versus numbers that tell me it's a tails. Now, in order to do that, I have to first look in at that probability. And honestly, it's going to be easier to look at that probability as a fraction for this situation. Half, 1/2. Probability of getting a heads when I flip a coin is 1/2. Probability of getting tails is 1/2. So, focusing in on that specifically, 1 out of 2. So when I get my calculator to create random numbers, that denominator, in this case 2, tells me the minimum number of the random numbers that I need to make the calculator produce. If I had things that were not all 1/2, if I had situations where I was working with 1/8 and 3/16 and 4/29, I would get the least common denominator amongst all of those, and that would tell me how many different numbers I need to make my calculator generate. We're not. We're dealing with coins. They're 1/2 and 1/2. They have the same denominator. Okay, so I need to make my calculator come up with 2 numbers, and I want it to come up with one of 2 numbers. Which numbers it comes up with doesn't really matter. I want them right next to one another. Oftentimes people do 0 or 1 or 1 or 2. Would you prefer 0 and 1 or 1 and 2? Doesn't make a difference. You just got to make a choice. 1 and 2? Okay, so I'm going to make my calculator come up with the 2 numbers, 1 and 2. The number of numbers that fit that actual heads versus tails is the numerator of those fractions. In this case, it's 1 and 1. So one of them has to be a heads, one of them has to be a tails. The number 1, is it going to be a heads or a tails? Doesn't matter, you just got to make a choice. Okay. I heard heads first. That means if your calculator shows a 2, it's going to be a tails. Okay. When I'm running a simulation like this, generally, I create a relative frequency table with an additional column in the middle of it. Relative frequency table, x equals number of heads. And I'm going to make it columns this time, and there's a reason behind that. Outcomes were 0, 1, 2, or 3 heads. Typically, the second column is P of x. I can't calculate the probability of x in an experimental way, because that's what we're doing. We're doing experimental probability right now. I can't do that unless I have the frequency of how many times something happens first. After I have that frequency, then I'll actually calculate the probability. So it's an augmented relative frequency table that I'm creating. Okay, so back to what I need to do to get my simulation to work. I need the calculator to tell me the numbers 1 or 2, since I'm flipping 3 coins, 3 times. That will be 1 trial in the situation. Now, I chose 72 trials because there's 24 of us in here, and I essentially said we can each do it 3 times. Because that requires clicking enter on your calculator another time, and I think you're good with that. So, to do this on my calculator, first up, pull up the calculator. Step 1. Okay. I'm going to use a random number generator. When you're doing it on a calculator, that is what you are using, is a random number generator. Random number generators show up in your probability menus. Now, we've used the probability menu on the TI and on the Casio before. Do you remember where they are? TI's got minimum places that it puts menus. It's under the math button. Scroll over, you'll find probability. On the Casio, it's under options. Scroll over, you'll find prob. And there was our factorial, our permutation, our combination, and the random stuff. Now on the Casio, I need to get into the random menu. On the TI, I'm already in the menu that I want to be in. We are going to make it come up with random integers. So rand int, which is F2 here, and it's 5 on my lower one. And it's yelling at me because I accidentally clicked a button. Now, your calculator might look a little different than mine. If you have a TI-83, your calculator is going to look more like my Casio than like the TI. If you got a TI-84, then it's going to do this. Lower and upper are the smallest number and the biggest number you want the calculator to give you. What's the smallest number we want the calculator to give us? 1. What's the biggest number? 2. So on the TI-84s, I do 1, I do 2. On the Casio, I do 1, start with the lower number, and then I do comma, and the same thing on the TIs. You do the comma. Comma on the Casios is above the delete button. On the TI-83s, it is above the number 7. And then I do 2, and I do another comma. 1, 2, smallest number, biggest number, and then the third number you put in, which it puts as N in the TI-84s, is how many times we want it to give us a 1 or a 2. How many coins are we flipping? 3. Click enter. On the TI-84s, you might have to click enter twice. And it should give me a list of numbers. Now, this is a random number generator. Should your numbers be exactly the same as mine every single time? No. Now, I'm just going to work with my TI, just because I'm a TI user. I got the number 211, which is 2 heads. I'm going to put a little tally there. I'm going to do this 3 times. 222 is 0 heads. 111 is 3 heads. Why am I doing it 3 times? Because we got 72 trials and there's 24 of you, and so every one of us is going to do it 3 times. And we're going to put our data together. Does that make sense? Okay? So, do it 3 times on your calculator and keep track of what you got for yours, because we're about to put it all together. And I'm going to be calling on all of you to answer things. That's because you're in the stats menu. Yeah. Max. Everyone got their 3 trials? Marissa, I'm starting with you, just because you're in the front corner. What did you get for outcomes?
1,
1, 1, 2. Izzy, what'd you get?
0, 2,
0, 2,
and 3.
3. 1, 2, 2. 1, 1, 1. Sorry? You're not done it yet? Okay, I'm gonna come back to you.
1, 1, 2.
Dom got 1, 1, 2. Bella.
1, 2, 2.
1, 2, 2.
1, 1, 3.
1, 1, 3 for Kale.
I got 0, 2,
Sorry, 0, 2, 3. A 0, a 2, and a 3. 1, 1, 1. 1, 1, 2. 1, 2, 3. Brody. A 3, 2, and a 1. 1, 1, 2. 1, 2, 2. Sorry, 1, 1, 2. Perfect. 1, 1, 2. You can do your routine. 1, 1, 1.
0, 1, 1.
0, 1, 1. 0, 3, 3. 3, 2, 1. 0, 1, and 2. 2, 2, and 1. How many did we end up getting your 3 tries? Or 2? Okay. I will show you how to do it afterwards. Okay, I'm going to do an additional 3, and I got, heads is 1s again, so I got 2, 2, 1. So, we ended up with 6 situations where we got no heads. 5, 10, 15, 20, 25, 30. 4 situations where we had 1 heads. 5, 10, 23 2 heads. And 9 3 heads. How do we find the probabilities? Yes. Okay, I'll send her down. Yep, thank you. Bye. How do we calculate the probabilities? That over, what is the total? 72. We did 72 trials. 0.0833. 0.4722. 0.3194. And 0.125. The only one that actually matched the theoretical was 3 heads. Would you expect them to match perfectly? No. But the last thing that finishes this up is, what if we kept going? What if we didn't do 72 trials? We did 700 trials, 7,000 trials, 7 million trials. What would you expect to happen? It would get closer to the theoretical. It's the last thing we talk about. It's known as the law of large numbers. Law of large numbers states that the more trials in an experiment the closer the experimental, I meant to say, probability gets to the theoretical probability. In fact, the law of large numbers, it's such a strong law, it's such a strong property of probabilities that in situations where calculating probabilities is super hard or nearly impossible, what they do is they do a lot of trials in order to calculate the probability, assuming if you do enough trials, if you do enough trials, then you've gotten to the correct probability. Okay, that is it for today. I've got a worksheet for you. I'm so mean. No, I wouldn't have assumed that was me, but that's what I had heard. Yeah, I caught that afterwards. I just didn't hear what you had said.